This tape presents our studies on robot motion planning in an environment with obstacles of arbitrary shape. It consists of two parts, one related to computer simulation and the other to experimental work. In our first experiment, we study human capabilities in spatial orientation and motion planning in a maze and compared with the performance of our algorithms. All this assuming tactile sensing. Here, a human subject is asked to move a point mobile robot using the mouse of the workstation from point S, the start on the left, to point T, the target on the right. What is shown presents a fast replay of the session that took about 15 to 20 minutes. When the robot hits an unknown obstacle, a small part of it appears in the screen so that the subject can start maneuvering around the obstacle. When the robot steps back from the obstacle disappears. Later, the whole maze will be displayed. Soon, the robot arrives at the target, and the length of the generated path, which is shown in the left bottom corner, is about 22 units. This is the same experiment, this time with the maze shown. Now you will see the performance in real time of our algorithm in the same operating the same input information. The path is shown as a red trail. The algorithm does not store previous points and thus requires very little memory independent of the maze complexity. As shown, the length of the generated path here is about 4 units. This section is similar to the previous one, except the human subject is asked to move a 2-link robot arm with revolute joints from the start position, which is the solid figure on the left, to the target position, the stick figure on the right. Again, this is a fast replay of the session that took about 15 to 20 minutes. When any point of the arm touches an invisible obstacle, this piece of the obstacle appears on the screen, so that the human subject can start maneuvering around the obstacle. Shown is the trajectory of the robot endpoint. The picture on the right shows the same motion in the configuration space. The length of the generated path is about 72 units. This is the same experiment, but with obstacles shown. This is the way that our algorithm proceeds, in this case in real time, using the same information. The path of the robot endpoint is shown in red. The length of the generated path is about 21 units. This is a pseudo 3D representation of the last experiment with the algorithm, which shows how a 3D SCARA arm would perform in this situation. This part studies the performance of motion planning algorithms, similar to those shown before, when instead of tactile sensing, range sensing or vision is used. What you see now is the performance of a human subject in this maze when he is using tactile sensing only. Next is the performance of the algorithm, again with tactile sensing. This is the performance of a similar algorithm, when the mobile robot can identify obstacles within a radius shown by the vertical bar in the right bottom corner. As one can see, the path length becomes shorter, and the real-time processing takes longer. The performance becomes even better when the radius of vision becomes larger. These preliminary results relate to applying range sensing to the case of a robot arm. Unlike a mobile robot, whose radius of vision can be assumed fixed, the quote-unquote vision for the arm manipulator, when transformed into the configuration space, becomes variable even if all sensors covering the robot arm have a fixed sensing range. Shown on the left is the variation of the minimum radius of vision in the configuration space when the arm manipulator in its workspace goes through the motion as shown on the right. This information then becomes the input for the real-time motion planning procedure. This is the second part of the tape. It consists of different sections related to the experimental work. In this two-dimensional study, the black acrylic bars containing about 80 infrared sensor pairs are installed on a Puma 560 arm and provide information about obstacles in the robot environment. The resolution and range of the sensor system is demonstrated with these simple experiments. Here, the robot is interacting with moving obstacles. The implemented motion planning algorithms are similar to those before. In addition to such algorithms, the real-life system must have means for real-time acquisition and processing of sensor data, and additional algorithms for planning every single step along the robot trajectory. In this experiment, the robot is moving from its starting vertical position to the target position, while avoiding two previously unknown obstacles. This is the target position. Here, the same motion, shown in the configuration space, appears on the screen of the Sun workstation. One can judge here the smoothness of the robot motion when maneuvering around obstacles. This part of the tape is courtesy of Neville Hogan from MIT and Wyatt Newman from Philips Corporation. As you can see, this planar arm manipulator proceeds swiftly to the target position shown by the experimenter's wand. When any of the four black cylindrical obstacles are encountered on its way, the real-time motion planning during the collision avoidance phase is done using our algorithms. The information about the obstacles is provided by a TV camera installed in the ceiling. This part of the tape shows experiments with three-dimensional robot motion planning using the infrared sensitive skin developed in our laboratory. This is the skin before the installation on the arm and before infrared sensors, about 500 of them altogether, are placed on it. Three such boards are used in the sensor system. As you can see, the printed circuit material is quite flexible and can be easily bent. Shown here are various views of the robot with the sensitive skin. There are no blind spots on the arm, thus an obstacle approaching from any direction will be detected. The intersensor spacing is less than 2 inches, depending on the curvature of the arm. Using a CCD camera that is sensitive to infrared light, you can see the pulsing of the LEDs. The scan rate is about 17 Hz. Thus, the entire skin is pulled once every 17th of a second. The sensor operates at a distance of up to 5 inches and uses amplitude-modulated infrared light for the detection, which increases its immunity to ambient light. To give the viewer some idea of the time multiplexing sequence, the scan shown here is slowed down approximately 15 times. Using the sensor data processing algorithms we developed, we cause the arm to move away from obstacles. This involves processing various local normals to the approaching obstacles. Since the arm may be interacting with more than one obstacle, the arm may need to process multiple local normals. Here the arm is interacting with two obstacles. The system can handle obstacles of arbitrary shape and size. As you can see here, the arm oscillates between obstacles. This can occur, as it occurs sometimes in nature. Such oscillations are dependent on the ratio of the sensor sampling rate and the arm speed. This effect can be controlled to various extent through internal parameters of the system. Since the sensor uses infrared light, the robot can work in a dark room. This was taken using the CCD camera. Although it is difficult to see the obstacle, you can guess its location when it occasionally occludes the arm. The robot on the left is holding a white object and executing two identical square-like motions. Notice the robot on the right, which is the one with the sensor skin, is moving away from the white obstacle held by the left robot. This is the start of the second motion, identical to the first. Notice the reaction of the sensor-controlled robot on the right is different for the case compared to the first. In this experiment, the robot is moving from its start position to its target position while avoiding an obstacle on its way. Next, it moves back to its original starting position. Notice that the arm motion around the obstacle is different from the first time. Here the same trajectory is shown on the workstation screen. On the left, a 3D perspective projection of the trajectory in configuration space. together with the accompanying two-dimensional projection. Below are two orthogonal two-dimensional projections of the same trajectory. This experiment is repeated viewed from another angle.